Hello everyone, how are we doing today? So today we're going to be doing some example problems analyzing some pedigree charts. So in the lecture, we went over pedigrees and how to read them and how to try to figure out what sort of disorder is running in that particular family. So today I have about 5 examples. I have 5 examples that we're going to go through, and you're just given the pedigree. So look at it, try to figure out, is autosomal dominant, autosomal recessive, X-linked dominant, X-linked recessive, or Y-linked. So based on what we learned so far in all the lectures building up to now, we can look at these and start mapping out different things in human genetics. So pedigree charts are, again, the big way we do human genetics and mapping things through a family history. All right, so on each one of these, feel free to pause it and try to figure it out yourself first. Look at it and think, what could this one be? Now, I'll give you well, the first one is one of the harder ones of it. So what do you first look at when you look at this pedigree? So I see all the males have it here. So all males have it. So all males. That is a little hint already. So all males tells you it could be Y-linked or it could be X-linked recessive. So let's look. That should be the first hint when you see that. So Y-linked, if it's Y-linked, if a male has it, all sons have to have it then too, because the male passes on the son. So if it is Y-linked, this father here, so 2-6, has to have it as well. He doesn't have it. So there's no way this can't be Y-linked. So it's not Y-linked. So let's cross that out. Other option here is a little different. It could be autosomal recessive. So if it was autosomal recessive, all of these would be homozygous recessive. So let's look at that and see if we can figure it out. If these are all homozygous recessive, then what would the other ones have to be? So for these to be homozygous recessive, both of these would have to be a carrier, which is possible. That's possible. And then this one could be anything. So remember, underscore means either dominant or recessive. So it could be recessive. But if we look at this, for this to be recessive, this one has to be a carrier. This one over here also has to be a carrier. Because if this is, little a here, or homozygous recessive, there's then a 25% chance of these offspring to have it. If this was dominant here, it'd be 0% chance. And over here, this one has to be a carrier as well to give another 25. Well, this one's a 50% chance. I wrote this one wrong. 50% chance over here. If you do that Punnett square, 50% chance. And this one, I meant to say, is a 25% chance. So these are two heterozygotes. So in order to get any of these offspring down here that have it, you have to have 2 carriers. So, I mean, a lot of these pedigrees, you could say, it could be this. Just as long as you can explain yourself correctly and have the correct reason, you'd get that problem correct. But it's a very low chance that you find 2 carriers of it, 2 heterozygotes here. So that's tough. So up here, this individual would have to be these. So it could happen. Yeah, it could happen, but not super, super likely. So let's look at another case that this could be. So if it's maybe not autosomal recessive, what if it's autosomal dominant? So if it's autosomal dominant, let me change colors here. So let's make this green now. So if it's autosomal dominant, this could be this, and all of these are recessive now. All of the non-carriers are recessive. But we hit a problem on this one right here. So if this one is recessive and this one is recessive, how do we have any down here? So this one would have to have a dominant form from somewhere. But if we look at this, it's all males that have it. And this is another reason that has me thinking it's not autosomal recessive. I think this one is autosomal dominant, but it's sex limited. So all males have it except for this one. Well, this female. All males have it, but this female does not have it. This female would have to have the dominant form. Would have to have that from that parent up there if this is autosomal dominant. So if this is the case, only the males present this trait, but the females do not if they have it. So we talked about a few examples in the lecture where this could happen. So again, can you explain your answer correctly? Like I said, you can have multiple answers for the same problem for these, some of the times, not all the time, just as long as you can explain your reasoning based on what we learned. So sex limited is an option, or incomplete dominance. So remember what incomplete dominance is? An example of that is polydactylism for multiple fingers and toes. So someone could have incomplete dominance, which is a dominantly inherited disorder, where the expressivity is different. So even though they have 5 fingers and 5 toes, they actually have the version of that disease, but they don't show the phenotype. So genotype doesn't always match genotype. That's incomplete dominance. So, the penetrance examples we did. So it could be that too. So this person just might look normal, even though they are actually a carrier. And then the rest of these tables would make sense. So here we'd have, this version, and then down here, each of these would be heterozygotes with the dominant version as well. So that's the first one. Like I said, the first one in this one was the hardest because it could be 3 different things almost. Just as long as you explain it correctly is all that matters on that one. All right, next one. So first thing I see red squares. So we see only males. So if it's only males, just like the last one, we want to look, is it Y-linked? No, it can't be Y-linked, because if it was Y-linked, this male would have to have it. Well, this male would have to have it, and this male would have to have it, not necessarily that one. So those males do not have it. This male would have to have it too. And this male does not pass it to that son. So it can't be Y-linked. So other options, let's check X-linked. So remember, X-linked recessive are more common in males than females. So X-linked recessive here. So a male would have to be this, and a female could be carrier. So we don't know yet. So let's just start down here. You start at a spot and start working your way around, making like little test crosses in a way. So this male here would not have it. This female would have to be a carrier then, which could happen. That female could be a carrier. And then up here, this male doesn't have it. This female would have to be a carrier for this female to get that X chromosome. And then up here, same thing up here. So you could see how this carried down through all these generations. So this female carrier gave it to that female carrier. Well, this carrier came in from somewhere else, didn't give it to that one. So carrier, then this one gave it to this one, and then finally the male presented it down here. And then if we look at the other side here, this female would then be a carrier. This male would not have it. Then we go down through here. This male has it. So here we have, apologies if you're a cat meowing. So here, little a comes from the mother. Then over here, this one would be another carrier. And I know this one's a carrier because both of these sons have it, and this male does not have it. So I don't need to do the rest here. For this one, this could be either way. So this one could be a carrier, might not be a carrier. So here you just write a little underscore. Now there's a chance, none of these present it down here, but there's still a chance where you're not 100% there. Yeah, so I'd say X-linked recessive for this one. All right, that's the second one. Let's go to the third one now. And the first thing we see here, we see equal frequencies. So an equal frequency of male and female. So males, females, equal frequencies. Remember, this line right here represents deceased. This P down here represents the proband. That's the person who initiated this genetic tree testing. Just a little reminder. And then over here, these represent non-identical twins. If there's a line here, they'd be identical twins. So just a little description there. So we see equal frequency of male and female. That makes you think autosomal. So start thinking autosomal. Then you want to figure out if you want to check if it's autosomal dominant or recessive. And one thing I notice here is that it does not skip generations. If one does not skip generations, check autosomal dominant first. Because usually, well, sometimes autosomal recessive skips generations. That's because it can be a carrier. So this is probably autosomal dominant. And males do not pass to all daughters, so it's not X-linked dominant as well. So the male, if the male had it, so say it was X-linked here, so let's say this male X-linked dominant had it, these females could also have that same thing. Because they'd get the X chromosome from their father, so they'd have, if it was X dominant, they would present the trait in that case there. So it's not X dominant, so we can erase that. So we think it's autosomal dominant, so it's kind of the same thing as the first one. So we check it here, and all of the non-trait showers are homozygous recessive, and most of the time these ones are heterozygous, because if this one was homozygous dominant, all of the offspring would present the trait, and we don't see that at all here. So I know all these ones are heterozygous. So same here. So you fill this in, and it all fills in and can work. So you can continuously pass this down through subsequent generations and see how it works. So yeah, autosomal dominant for this one. I don't have to fill in the rest. They're pretty obvious of what they would be. All right, another autosomal dominant. Next one. This is the interesting one. Well, they're all interesting. This is just the one that throws in a few other curveballs at us. So this is a messy chart. Down here, we see the fourth generation, 1 female and 4 males. Got it. So you can't necessarily go automatically X-linked, dominant or recessive, because a female does have it. And for this female to have it, this male would have to have it too. So this male would have to present the X-linked recessive, and this female would have to be a carrier of it. And this male doesn't have it, so it can't be X-linked recessive for that reason. So what else? What other options do we have here? So what happened here is these two, this first generation, they both had 2 kids. Both these families had 2 kids, and then the siblings married each other or got together. So this family's daughters got together with this family's sons, and then they had kids that then got back with each other. So this is a consanguineous thing. So these would be cousins, and not only cousins, but close. They're almost partly siblings at this stage here because of this crossing up here. And then we finally see this phenotype present itself in the 4th generation. So my guess is that this is likely autosomal recessive. Why do I think that? Because it hid in all these subsequent generations. We just went over why it's not X-linked. It's because this 3-4 here has an affected daughter. Since he has an affected daughter, can't be X-linked. So if we're checking autosomal recessive, these are what the options would be. You know, these all would be little a's, of course. This one would be homozygous recessive 2. We go up here and check the parents. These ones don't present it, so each of these would have to be heterozygous. Same with these parents here. Each of these would be heterozygous. Now's where it would be more of a guessing thing, unless you do actual testing of what these parents are up here. So these are each heterozygous. Neither of these have it. So my guess are each of these are heterozygous, which they should be. There's just no one expressed it. One half has to be. One has to have the recessive trait. The other one doesn't have to have it. So let's go with that. because this still has, the chance of heterozygous here. And then over here, same thing. So these ones also had it too. So it could be the same thing over here where, let's say the sons from this family were each carriers. So and up here, again, we're not 100%. Not 100% on what this other one could be. But then over here, we're tracking it back. One of these could have come from, well, this one, again, you're not 100%, but one of these has to be a carrier up here. So this all could have started with one parent in this first generation here being a carrier. All these other ones could be dominant. Could be dominant. Homozygous dominant. And then, but just as long as this carrier kept going through the generations and each of these children ended up heterozygous, it will continue passing down, because this is the danger with consanguineous matings or incest, is that then here is when the phenotype finally expresses itself. It takes this long, but because you kept all the genes interacting with each other, that's what increases the risk of these genetic disorders within these sorts of groups. And you can see that, and lots of examples of that. All right, last one here. Alrighty, so first generation, second generation, third and fourth, I see a big mixture of males and females, so an equal frequency here. So that pushes us away from X-linked. So now ideas are autosomal dominant or recessive. And again, here are some twins. Neither of these parents have it, so that makes me automatically go autosomal recessive. But there's no skip to generations. It could be autosomal recessive. So say both these parents started out as heterozygous, there's a 25% chance of, homozygous recessive. So these were non-identical twins here, and they both would have it. This child would have it, and this one would as well. This one could be either, and this one, okay, those are the children. It's just tough, because look at this. This is 1, 2, 3, 4 of their 5 kids had this trait, but there was a 25% chance. So 4 out of the 5 children had got, that disorder when there was only a 25% chance of getting it. Those are tough statistics. So another thing about this is that we don't know the information about these parents. I forgot to put lines through these. So you're not sure. You can't go back into history and ask them if they had a disorder, do genetic testing, or anything like that. So you're not sure on that. And again, over here, this would have to be heterozygous then, for then a 50% chance of both of these kids to have it. And the frequency that we see this disease coming up in all of these children here tells me it's less likely this is autosomal recessive. And the fact that we don't know much about these first parents here makes me think this is autosomal dominant. So it makes a lot more sense if we go back and map this out via autosomal dominant. I'll just choose a different color here. I'll just go back to green. So if this was autosomal dominant, it'd make a lot more sense if we're going back through here, because then all of these say we don't know if one of these parents had it up here. So one of these might have been fine. Well, let's say this was one parent that was fine, and then the other parent here had it. Remember, green. We're talking about the dominant form here. So if this parent had it, we just don't know enough about the history of the family to know for sure. But the frequency that we see the disease prevalence, it doesn't skip generations or anything like that. You don't really see carriers hiding it. Makes me think autosomal dominant. Again, you can explain the reasoning. You just have to go back to that first generation and say it would have to be this or it would have to be that again. But you could reason through this there is a problem, a statistical chance that autosomal recessive works. But I would say autosomal dominant is more correct. Alrighty, that is the last one we have there. I just realized a lot of these ended up being autosomal dominant. So, but I hope it helped you learn how to read these charts. So here, this one, all males. If I had this one colored in here, we go back to this one, That would suggest that, and this one over here, that could be holandric then. Every male passed it to a male child. So be able to interpret it, read them in different ways, and you should be great here. All right, that's all I have for the example problems. I know this went on a little longer, but I wanted to go into deeper explanation into the different ones. But let me know if you have any questions, and I'll see you all next time. Bye-bye.